Hello, this is part three of my video series on essential theorems for harmonic astrology. And in this video, I want to prove for you two methods for calculating harmonic charts. So let me see if I can share my screen here and we will get started. And I have to, as usual, get rid of a few panels so I can see what I'm doing. This will take just a minute. Just about there. And we're ready. So, essential theorems for harmonic astrology, part three, quantitative, calculating harmonic charts. All right, before going any further, we need to develop some rules for quickly determining the R harmonic for any angle in the zodiac. Prior to proving theorem one, however, let's work through a simple example that will illuminate the method of proof we want to follow. Thus, suppose we want to convert 245 degrees to its value in the 2 harmonic, the second harmonic. Remember that in the second harmonic, we take our 360-degree zodiac and we replace the first 180 degrees by one sub-zodiac, and then we replace the second 180 degrees by another sub-zodiac. Okay, well, we first need to determine how far into the appropriate sub-zodiac 245 degrees has gone. We can do this by first computing 245 degrees modulo 80, and that is going to give us 65 degrees. This tells us that 245 degrees has traversed 65 degrees into the second sub-zodiac that in the second harmonic replaces the 180-degree interval from Libra through Pisces. To find the value of 65 degrees in our sub-zodiac, we can now set up a simple proportion to solve. We'll have that 65 degrees is to 180 degrees as x is to 360 degrees. Solve this proportion and we get that x is 130 degrees. Okay, the proof of theorem one that follows simply mimics in a more abstract manner the proportion that we just solved. Theorem one, let x be an angle with 0 degrees less than or equal to x less than 360 degrees. Let r be a positive rational number. And suppose we want to find the value x sub r of x in the R harmonic. Then the root R harmonic angle, 360 degrees over R, is also the angle measure that will be replaced by a subzodiac. And our claim is that x of r is equal to r times, parentheses, x modulo 360 degrees over r, parentheses close. Okay, proof. Clearly, x modulo 360 degrees over r, all divided by 360 degrees over r, is equal to x of r over 360 degrees. That's clear, right? Well, if it isn't clear, just go back and look at our example and you can see where things fit in. So up here we have x modulo 360 degrees over r. That is corresponding to the 65 degrees here, which was 245 degrees modulo 180 degrees. The 180 degrees here, that is 360 degrees divided by our harmonic 2. Okay, and then the denominator, we've got 180 degrees, so that was 360 degrees divided by 2. And that's exactly the same sort of thing we have here. Instead of 360 degrees divided by 2 here and here, we have more generally 360 degrees divided by some harmonic r. And we set that equal to x of r over 360 degrees. X of r is going to be the new value that we're looking for in this R harmonic, the value of x in the R harmonic. And that is what we had right here. We're looking for the value of 65 degrees in this 360-degree zodiac and the 2 harmonic. Okay, well, once we understand this equation right here, we just need to solve it for x of r. So you can multiply both sides by 360 degrees. That's what we have here. You can flip this fraction down below. The r goes up in the numerator, and 360 degrees over 360 degrees cancels out. That leaves us with r times x modulo 360 degrees over r equal to x of r. And that's what we want to prove. Now notice in the calculation here, you first have to find x modulo 360 degrees over r, then you multiply by r. You don't multiply by r first, at least not in this theorem. Whether that works, multiplying by r first works or doesn't work, that's a whole different thing. But what we want to prove, you do the calculation in this order. First, you simplify this expression inside parentheses, and then you multiply by r. Okay. A common application of this theorem is when we're replacing each 30-degree sign with a 360-degree zodiac from Aries through Pisces. That would be what we do when we're looking at the 12 harmonic. So, to give an example, my sun is at 2 degrees Gemini, which places it 62 degrees from the beginning of Aries. However, I don't really need to know that in this case because since 30 degrees is equal to 360 degrees divided by 12, our harmonic is 12, which is, of course, equal to 360 degrees divided by 30 degrees. And 62 degrees modulo 360 degrees over 12, that's going to be 62 degrees modulo 30 degrees, which is equal to 2 degrees. If you divide 62 by 30, you get a remainder of 2. And that is going to be the degree measure within the sign of Gemini. Hence, the value of 2 degrees Gemini in the 12 harmonic is simply 12 times 2 degrees equal to 24 degrees. And that's going to be 24 degrees of Aries. To give another example, my moon is at 27 degrees Taurus, and so its position in the 12 harmonic is 12 times 27 degrees, which is equal to 324 degrees. But 300 degrees is the start of Aquarius. So 324 degrees is equal to 24 degrees Aquarius. Again, the formula above is very handy for when one wants to convert a position with a sign to its zodiac position in the 12 harmonic. It's handy because all you need to do is take the number of degrees in that sign, multiply by 12, and the result is automatically going to be less than 360 degrees or less than or equal to. Let's see, I think it comes out exactly less, but most people probably compute harmonics using the formula shown in Theorem 2 on the next slide. Theorem 2. Let x be an angle with 0 degrees less than or equal to x less than 360 degrees. Let r be a positive rational number. And suppose we want to find the angle x of r of x in an r harmonic. Then x of r is equal to r times x modulo 360 degrees. Notice this time we can do r times x first. That's inside the parentheses. So we just take that angle that's greater than or equal to 0 degrees less than 360 degrees, multiply by our harmonic, and then reduce the result modulo 360 degrees. Okay, let's take a look at this proof. Well, by Theorem 1, the value x of r we're looking for is equal to r times parentheses x modulo 360 degrees over r parentheses close. However, notice that we can rewrite our original angle x as x times w times 360 degrees over r plus x times r plus x modulo 360 degrees over r, where w is a whole number. Now, all we're saying here is that if we look at this angle, 360 degrees divided by r, whatever that angle might be, if you divide that into x, it's going to go into there a whole number of times. If it goes in there 0 times, then w is 0, and this part right here, that's the remainder that we get. If it goes in more than 0 times, then w comes out to some natural number, and we have just a natural number times 360 degrees over r plus this part, the remainder. Now, as an example of this, suppose that x, again, is 62 degrees, which corresponds to 2 degrees Gemini, and let r equal to 12, so that 360 degrees over 12 gives us back 30 degrees. Then 62 degrees modulo 30 degrees is 2 degrees, and we can write as per our formula that 62 degrees is 2 times 30 degrees plus 2 degrees. Okay? Now, continuing with our proof, notice that r times x modulo 360 degrees, well, r times x is going to be r times this expression I have up here. So we take r times that expression inside our brackets, and then you can multiply through by r. R over r cancels. You get r times this expression parentheses, and you wind up with w times 360 degrees plus r times x modulo 360 degrees over r, this part being in parentheses. And whatever all of this in brackets comes out to be, you reduce that modulo 360 degrees. Well, I claim we can just throw away this term, w times 360 degrees. And why can we do that? It's because w is a whole number. And when you do w times 360 degrees, and remember, we're going to simplify the final result modulo 360 degrees. So w times 360 degrees, that's simply telling us how many times we go around our clock face. And every whole number of times you go around the clock face just takes you back to the beginning, back to 0 degrees. So that part doesn't contribute anything. And we're only going to be left with this part here, r times parentheses x modulo 360 degrees over r, parentheses close, and you simplify that modulo 360 degrees. That works since the remainder, when we divide w times 360 degrees by 360 degrees is 0, and so this term here just disappears when we do it modulo 360 degrees. Furthermore, notice again that by theorem 1, r times parentheses x modulo 360 degrees over r, parentheses closed, that is equal to x of r, the value we're looking for, and where 0 degrees is less than or equal to x of r, less than 360 degrees. Now, since this angle is going to be less than 360 degrees, it follows that x of r modulo 360 degrees is just x of r. Okay, hence r times x in parentheses modulo 360 degrees. That's this thing right here that we're calculating. That is going to be equal to r times parentheses x modulo 360 degrees over r, parentheses close, modulo 360 degrees. That's what this line, this derivation right here concludes. But let's see, r times x modulo 360 degrees over r, you've got that up here. That is the angle x of r we're looking for. So you get x of r modulo 360 degrees. But this angle x of r is going to be less than 360 degrees. So modulo 360 degrees, you just get back the same thing, x of r. Now, the formula developed in Theorem 2 is probably the one that most people use when calculating harmonics by hand. For example, instead of using the result of Theorem 1 to find the 12 harmonic of 27 degrees Taurus by calculating 12 times 27 degrees equal 324 degrees equal 24 degrees Aquarius, as we did before, we can simply multiply the measure of that angle from 0 degrees, specifically 57 degrees, by 12, and then express the result modulo 365 degrees. This gives us 12 times 57 degrees modulo 360 degrees equal to 684 degrees modulo 360 degrees equal 324 degrees, which again is equal to 24 degrees Aquarius. The same result obtained previously by using Theorem 1. Okay, that is going to be the end of part 3, which shows you how to calculate harmonic charts by hand. So let me stop sharing my screen, and I'm back. So I hope that makes the proof, that walkthrough, I hope it makes the proof a little bit more understandable. And I hope you join me again for my next video in this series. But for now, I'll just say so long and be well.